So as I said, in the book, problem 43-ish is really got a 6 here as opposed to an 8. But the first thing we'll start with is the domain of this function. The domain starts out as everything, and then you kind of restrict it to places where the function is well defined. Now, in our case, the problem that we could run into is because we have the square root. What problem could you see with a square root? Yeah, you don't want it negative underneath the square. You want to ensure that it's positive. So if that's the case, we need to make sure that 8 minus x is greater than or equal to 0. Now, it can equal 0 because you can take the square root of 0. So that means x is greater than, or 8 is greater than or equal to x. I don't know why, but I like it better if the x is on the left-hand side. It's just easier to interpret. X has to be less than or equal to 8. So our domain is negative infinity to 8 brackets. So that's your domain. So if you come up with some kind of a critical point that's outside of this, you ignore it because it's not in the domain of the function. Well, let's see if we can't figure out a few things about this graph and where it has its maximum points and stuff like that. So we'll start by finding its derivative. And to that end, I'm going to rewrite this as 8 minus x to the 1/2 power. Okay. Let's work on finding h prime of x. What rule do I have to use to find h prime of x? Chain rule, and what else? Product rule. So you've got your first and your second. We need f prime g plus g prime f. F prime I hope you can do without too much sweat, right? That's just a 1 times 8 minus x to the 1/2 plus f times g prime. Now for g prime, you already just told me that we got to use the chain rule. So let's use the chain rule first. So that means that the 1/2 is going to come out in front. 8 minus x to the negative 1/2, right? Multiply out in front, subtract 1 here. Times what? Times a negative. Basically negative 1 here, because it's the derivative of the inside. So we've got the derivative of the outside times the derivative of the inside. Let's clean this up a little bit. That's 8 minus x to the 1/2 minus x over 2 times 8 minus x to the negative 1/2. Exactly. So this is the stuff we just practiced a little bit. You want to factor out the term with that largest negative exponent. So in this case, it's going to be 8 minus x to the negative 1/2. Now, I'm not sure I really got much of a consensus from you, so I'll factor this out this way. 8 minus x to the negative 1/2. And the remaining terms have to get divided by that term that I'm factoring out. So 8 minus x to the 1/2 minus x over 2, 8 minus x to the negative 1/2. And both of these terms get divided by that term that I'm factoring out. So that is divided by 8 minus x to the 1/2. Negative 1/2, thank you. So that gives us some quick simplification, at least for part of this. Because right here, those two terms are the same. So that just drops out of sight altogether. But how about here? What happens when I divide 8 minus x to the 1/2 by 8 minus x to the minus 1/2? Yeah, you get a 1. So you get 8 minus x to the first power minus, the only thing left from here is x over 2. Okay. Well, in these brackets here, I've got like terms. I've got a coefficient of -1 and a coefficient of -1/2. So overall, that's -3/2 when you put that together. So I'll rewrite this as 8 minus 3/2 x over 8 minus x to the 1/2. So I put that term in the denominator. Okay. Well, I can find the critical points now. Where are the points where I'm going to have issues with respect to this function? So the critical points, well, what defines a critical point? What do I have to look for with respect to the derivative? Thank you. Where it's 0 or undefined. So where it's 0, h prime of x is going to be 0 when the numerator is 0. So when 8 minus 3/2 x equals 0. Or 8 equals 3/2 x. And the fast way to solve here is to multiply both sides by the reciprocal of 3/2, which would be 2/3. So we'll do that on both sides. 2/3 and 2/3. All that will cancel out on the right-hand side. That leaves me x and 16/3 on the left-hand side. What about where it's undefined? It's where the denominator equals 0. Where 8 minus x to the 1/2 equals 0. Well, that's just going to be when x equals what? 8. So those are your critical points. Here, without looking at the graph, I think that's going to be a vertical tangent. And here, that's going to be either a maximum or minimum point. We've got to figure out which. But for the moment, we're looking okay here. Any comments or thoughts on our critical points? We good with those? Brandon? So where the numerator equals 0 is where you're going to have a point where the function flattens out. Either you're going to have a minimum or a maximum or maybe an inflection point. But where the denominator equals 0, that's where you're going to have a vertical asymptote or a tangent. Yeah. All right, appreciate the question. Anything else on this much of it? Courtney?
Yeah, so wait, can you please go over again how you got 8 minus 3/2 x?
Oh, sure. So it's right here. You can think of this as -1x, and this is -1/2 x. So you just combine the like terms. So -1 and -1/2 gives us -3/2. Yeah. No, I appreciate the question. Thank you. Let's keep going. I'm not going to take the time to show you the calculation of the second derivative. Let's just say it's a lot of fun. I enjoyed that part of my weekend. All right. So I'll spoon feed you this. 3/4 x minus 8 over 8 minus x to the 3/2. So that's our second derivative. Kind of like before, we're going to have problems at x equal 8. We know that. But more importantly, where's the root of the numerator? So if I want to figure out where this is equal to 0, I know where it's undefined. Where is it equal to 0? Where could I have an inflection point? Well, 3/4 x minus 8 equals 0. 3/4 x equals 8. It's all right. So multiply both sides by 4/3, and as you said, we get 32/3. If I wanted to write this as a mixed number, what would it be? Ten and 2/3. Can anyone see a problem with 10 and 2/3? Yeah, it's outside of our domain, right? Remember we started this out and said, oh, our domain is everything less than or equal to 8. So this is outside the domain. Yeah, so basically this function can't change signs in the domain. It's either always going to be positive or always going to be negative. We just got to figure out which. So let's start putting some of these things together. Now how about 16/3? Is 16/3 in the domain? Yes, it is. So it's a little bit more than 5. It's 5 1/3. So 16/3, and at 16/3, the function was 0. I'm not going to worry about the point at 8 because 8 is right at the end of our function. So, I mean, there is some interesting stuff happening there, but we'll figure it out here. So this is for our first derivative, and then I'm going to do another one for our second derivative, which is going to actually look kind of funny. Because we don't really have a point that we can test, right? Or it's not, or test around. So just pick anything. Pick anything you want, and it'll work. So we'll come back to that in a minute. Do we need practice putting this into our calculator and testing the points? I'm happy to do it. Okay, so let's do that. Now keep in mind, 16/3, like I said, is 5 1/3. So as far as test points, you could use, say, 5 to get something to the left and 6 to get something to the right. We'll start by putting that function in. Now for myself, I think it's going to be handy to use the second key and then the alpha key to give myself a fraction. So it's 3/4 x minus 8. You know what? I screwed up. Sorry about that. Let me start it again. Let's see. So I'll do alpha y equals, and then I'll do 0.75 x minus 8. So that's my 3/4 x minus 8 divided by parentheses x minus, or 8 minus x raised to the 3 divided by 2 power. So pretty ugly expression, to be very honest. But it is what it is. That's our derivative. Oh, you know what? That is the second derivative. That's the second derivative. All right. Let's also put in the first derivative while we're at it. First derivative was back up here. So put that one as well. Let's think here. So I'll do the, and I'll do it old school here. Let's just do it as 8 minus 1.5 x parentheses divided by parentheses 8 minus x parentheses raised to the 0.5 power. You could also do the square root down there. It doesn't matter. So I've got both my first and second derivatives in there, just so that we don't confuse ourselves. I'm going to go back up here and shut that off. Shut that graph off. In fact, I'm not going to look at the graph at all, but I don't even want to look at the function. Let's deal with the first derivative now. So if you go to the equal sign and press enter, it'll shut that function off. So that now we're only working with the first derivative right there. Let's go to our table. Your table should be set up like this. And let's test some points. I think we said 5 and 6 worked okay. What's the information that I need out of this? Good. Positive and negative. So that's what we're looking for. Positive and negative. Positive and negative. What's that tell us about the graph of the function at this point? And if something's increasing, then decreasing, like that, the first derivative test tells us that this point is a local max. Good job. So this is a local max, at the very least. Now let's go for the other one. So I'm going to go back here to y equals. I'm going to turn this graph on. You do that by pressing the enter key. And then let's shut the other graph off. Again, by putting on the equals sign and then pressing enter. So with the first one on and the second one off, let's go back to the table. Delete those values. It doesn't matter. But we need to pick any value. And it doesn't matter what value you choose. Because essentially, this function can't change signs at all over the domain. Well, at 8, the function stops. Anything less than 8 would be a good choice. So you could choose like a 0 if you wanted to. Keep it simple. 0 gives us something negative. So we chose 0, and the second derivative was negative. What's that say about the shape of the graph? Concave down. So the graph is always concave down. It never changes. It can't change. The only place that this could change signs is outside of the domain of the function. So it's always concave down. Let's see if we can't match this with the graph now. All this information should blend together. All right, I'm going to shut off those graphs and actually graph the function x and the square root of, let's see, x and then the square root of 8 minus x. Now let's see. As far as my window is concerned, I want to see that graph, say maybe from -5 to 8. And I'll keep the settings on the y-axis the same, -10 to 10. Let's hope that this covers what we need. Ooh, perfect. Wow, nailed it. All right, so there we go. Our graph passes through the origin, which we can see when we look back at the original function. The graph is always concave down, and it has a maximum point right here. Now we know the x-coordinate. Let's see if we can't figure out the y-coordinate. If you hit the trace key and type in 16 divided by 3, it should tell you that the y-coordinate is about 8.709. So that'd be your maximum. If I was asking for the y value, that'd be at 8.709. That's your max. All right, cool. So that's bringing like everything together on that one. Drew, question? No good? All right. Any other thoughts or feedback on problem 43-ish? Eureka? Sure. So the 8.709 is going to happen when x is 16 over 3. So yeah, there's a couple ways you could do it. I mean, I did it by tracing the graph. If you hit the trace key, then you can type in a number like 16 divided by 3. And when you press enter, it gives you the x and y coordinates. There's your 16 over 3, and that's your y coordinate. This is the original equation. So if you look back, this is what I'm graphing right here. Alternatively, you could hit the table function. You can go to table and type in 16 divided by 3. And it gives you the first few digits here. If you want more digits, cursor over there, put the cursor on the y value, and you get all the digits that you could want. All right? Appreciate the question. Anything else on this one? All right. So that was a kind of a lengthy problem, but it had a couple important things that I wanted you to see there, including factoring this thing out. This is something that I want you to be able to do. And we'll do a few more examples like this today so that you're competent at it. I'm not saying you're going to love it, but hopefully you'll be comfortable with it. No, there's one more that we're going to do. It's problem 36. In fact, I think I might have put this on your handout from last week, but I don't have a copy handy for myself, so I'm going to look at it in the book. Maybe I do have a copy. Yeah, here we go. No, it's appreciate it. I got one. So again, this is a reasonable problem because it's just asking you, do you understand some of these things? In problem number 36, they say, on what intervals is f increasing and decreasing? And let's start there. So here's our function. Problem 36. F is increasing. Well, let's assume that the function starts at 0. Where would f be increasing? From 0 to what? All right, from 0 to 2. But that's not the only intervals where it's increasing. Sarah, where else is it increasing? Yeah, 3 to 5. Good, 3 to 5. And there's one last one. That'd be here, from 7 to 9. You know, I'm just going to limit myself to what we can see here. I mean, the graph probably continues that way towards infinity, but we'll just limit ourselves to what we see here. Now, the function is also decreasing in certain intervals. F is decreasing. And those intervals are just going to be the complement of where the function was increasing. So where is the function decreasing? Thank you. 2 to 3. And 5 to 7. I think that's it, right? There and here. Okay, good. What else do they ask us about this one? It says, at what values does f have a local max or local min? So, local max. And in my way of reading this, it says, at what values of x does it have local max or local min? So it's looking for the x values, not looking for the y values. So this is part B. Local max would be at 2, and where else? X equal 2 and 5. We have a couple local mins. Yeah, 3 and 7. Drew? Sure. It says, on what values does on what values of X does F have a local minimum or a local maximum? Talking about F, yeah. Oh, you know what? Oh, God, wow. I blew this. I didn't realize that this was F prime. Wow. Well, that's cool, so we can do it all over again. That actually makes it kind of interesting, though. It makes it a much more interesting problem because, I mean, as it was, it's kind of like, stuff that you know. But, well, no, you got them right, so that's good. So let's take a look here. A. So, where is it increasing? Now, what has to be true if a function is increasing? What's true about the derivative? Has to be positive, right? So, the function is positive between what and what points? F is increasing 1 to 6. Where else? 8 to 9. This is much more fun of a problem. Thanks, Drew. F is decreasing. Yeah, 0 to 1. And 6 to 8. Now we got to think about this next part carefully. Here the function has a negative derivative, and here it has a positive. So what's happening to the function? If its derivative is negative, it's doing what? Decreasing and then increasing. So Noel, what kind of a point has to be here at x equal 1? Good. Good. It's a minimum. Min. Now the next place that we have a transition is over here at 6. The function has a positive derivative and then a negative derivative. So, Keith, what would it say here if we have a positive derivative and then a negative derivative? X equals 6. What kind of a point is here? Inflection would be if we had a graph of the second derivative. So, I mean, this actually could be an inflection point, but I think actually it couldn't be an inflection point. Yeah, it's just a min. So you're going from no. You're going from increasing to decreasing. So your function is going up and up and up, and then it starts going down. So from increasing to decreasing has to be a max. And there's one more point that we have to deal with, one more critical point. That's at x equal 8. Again, the function's negative here, positive here. So what's going on with this point? Yeah, this is going to be a local min because it's negative, then positive, it's decreasing, then increasing. So x equal 8 is also a min. Yeah, I like that one a lot better. Yes? Because this is the graph of the derivative. So the derivative has a maximum here, but that's not what we're really trying to work with. We're trying to work with the graph of the function. So we have to kind of think a little bit beyond this graph here. This graph tells us a lot about the function. So it's increasing a lot right here, but then it starts increasing slower and slower and slower. And what would happen is if you had a graph of the second derivative, you'd see that. There'd be a change in the graph of the second derivative because it's no longer increasing as much. Okay. Let's see, what else? In fact, that's the next question. On what intervals is f concave up? So, yeah, that one's going to get a little harder because you have to think through the graph of the derivative. So f is concave up. Well, what's it mean when the f is concave up? What's true about the second derivative? It's greater than 0. Okay. Now, we've already got the graph of the first derivative. The second derivative is going to be the derivative of this graph. So I want f double prime to be greater than 0. That means that when I differentiate this, I'm going to get something positive. Well, this is going to be positive where it's increasing, right? So it's increasing from 0 to 2. That's where it's increasing, so if I took the derivative here, it would be an increasing function. Then what happens? F is, let's get rid of that. F is concave down. So that means f double prime is less than 0. Now, if f double prime is less than 0, that means that the derivative function itself has to be decreasing. Where is the derivative decreasing? From where to where? From 2 to 3. So, yeah, it's concave up here from 3 to 5. And see if you can't finish it off. Finish figuring out where it's concave up and concave down. What's that?
We were just talking about where f is, when we first started, and we're like, oh, we made a mistake. It's the same as it is the double derivative.
Oh, interesting. So what's next? What's coming up next here? Phil? Oh, sorry. Sorry, I already did it. Yeah, 5 to 7. So from here to here, the function's decreasing. That is, f prime is decreasing. So the derivative of this is going to be f double prime. That means the function itself is concave down, 5 to 7. And last but not least, here f prime is an increasing function. So from 7 to 9, f double prime is going to be greater than 0. No, you're spot on. The function, in terms of its concavity, is behaving like we originally thought, where the function was increasing and decreasing. I'd like to say yes, but I have to think about it a little bit more carefully. Yeah. Okay. Let me call it quits for this section here. And we'll see you in about 8 minutes.